A uniform ladder of weight W leans without slipping against a wall, making an angle theta with a floor as shown above. There is friction between the ladder and the floor, but the friction between the ladder and the wall is negligible. The magnitude of the friction force exerted on the ladder by the floor is... Let L be the total length of the ladder. There are several ways to attack this situation, but the fastest one is to first consider the equilibrium of forces in the vertical direction, which tells us that the normal force exerted by the floor must be equal to the weight of the ladder W, since there are no other vertical forces in the system. Remember, they told you that the wall is frictionless. So, the normal force is equal to W. And we have a free body diagram as shown. If we place the axis of rotation at the point of contact with the wall, we do not need to consider the unknown horizontal normal force due to the wall. The torques on the system are occurring as follows. W producing a clockwise torque at L/2 from the axis, and the normal W producing a counterclockwise torque at L from the axis. Finally, the friction force must be acting to the left, because the only way it produces equilibrium is that its torque is clockwise. Also, the torque for the weight and the normal force involve the angle 90 minus theta, because the forces are vertical. However, sine of angle 90 minus theta is the same as cosine of angle theta. So the equilibrium equation for torques goes as follows. W times L times the cosine of theta is equal to W times L/2 times cosine of theta plus friction force times L times sine of theta. The length L cancels out of the equation. We can then solve for friction force times sine of theta is equal to W/2 times cosine of theta. Therefore, the friction force is equal to W/2 times cotangent of theta, which is option E.